Hello everyone, this is chapter 8.3 and here we'll be discussing conditional probability, intersection, and independence. First I want to start off by talking about what is called a tree diagram or probability tree. Tree diagram is really meant for accounting, which we could have discussed in chapter 7, but I chose to handle that by the slot method, is the way we approach those problems. But if you go back, you can actually handle those types of situations by this tree diagram method. And here I describe a little bit of what the tree diagram really is, or at least the setup anyways. And here I say a branch is drawn for every possible decision for a given experiment. Now we're just going to dive into an example and then we'll actually see how it's used. So here the setup is that there are two balls to be drawn in succession, so one after the other, without replacement. So every time you pick a ball out of the box, there's one less ball in the box. Now the box contains 3 blue balls and 2 white balls. And the first part of this question asks us, how many ways can a white ball be drawn on the second draw? So the way I'm going to start doing this is I'm going to create these 2 branches like this. The first branch will represent me doing one of the tasks, which is, well, we're picking a ball. So if you pick a ball, there are 2 possible ways you can go for the first draw. Either you can draw white first or blue first. Okay? So this branch represents the 2 possibilities as far as which event will happen. So then, for the second ball being drawn, there's 2 possibilities for each of these, isn't there? There is drawing white second after drawing white first, or blue second after drawing white first, and similarly for the second draw after drawing blue first, there's white and blue as possibilities. Okay, so now in addition to labeling the branches by W and B for white and blue, I'm on the top of each branch going to label how many ways we can do such things. So how many ways can you pick white from your first draw? Well, there's only 2 white balls in the box at the very beginning after the first draw. Well, at the first draw. And there are 3 blue for the first draw. Okay, so now this is where things get a little weird and you kind of have to think about what's going on. So let's just imagine for a second. So if we pick 1 white ball, so that's what this represents. We picked one of the 2. So that means if we pick 1 again, how many ways can we pick 1 again from the box? Well, there's only 1 left in, so there's only 1 way to pick that 1 that's in there. Similarly, if you pick one of the 2 white from the first one, for the second draw, since there are 3 blues left in, there's only 3 ways to pick blue after you pick white first. So you could think about it for a little bit, but that's really what it is. So similarly, if you draw a blue first, well, there's 1 less blue in the box, so there's 2 for blue that can possibly be drawn. But for white, well, white was 2 from the very beginning. Since we didn't pull a white out in this scenario, then there's still those 2 left in the box. So these represent these alternate scenarios. So there are a lot of like what ifs in this situation, which is kind of the reason why I didn't want to discuss it for chapter 7, because I think it's a little too confusing. I mean, it's definitely doable, but the slot method kind of makes this a little simpler. And you'll see why this method was applicable before, because really this is just the multiplication principle of counting. Because now what we're going to do for each of these is we're actually going to multiply the branches that lead to the end path. So here it's 1 times 2, so there's 2 ways to draw white, then white. Here, white then blue, there's 2 times 3, so 6 ways to draw white and blue. 3 times 2 for this third branch path is 3 times 2, so it's 6 ways to draw blue then a white. And then for blue, there's 6 ways, 3 times 2, to draw blue then a blue. So this is the full tree diagram here. We can use this to answer any scenario, but the specific scenario we're given, now we can consider that, is how many ways can white be drawn on the second draw. So it's either drawing white then white or blue then white. So really I'm just looking at this. So if you add those together, either you drew white then white or you drew blue then white. So there's a total of 6 plus 2 different scenarios, because remember, or means you add those, because that would be the addition principle of counting. So in any event, here we get 8 as our answer. So 8 ways of drawing white on the second draw. Okay, good. Now, for finding the probability of drawing white in the second draw, kind of the same question, but there's a little bit of a different way of handling this. I'll have to create another tree diagram, but Yeah, that's fine. I'll draw it down here. It may get a little cramped, but I think we can do it. So we can draw white first or blue first, and then white second or blue second for each of those given paths. Good. But now up on top, let me draw this in blue instead of in red, are the probabilities for that given situation. So like here, for example, the first branch, well, how many ways can you draw one white? It's 2, but out of how many possible draws, there's a total of 5 balls in there. 3 plus 2 is 5. So the possibility of drawing white in your first is 2 out of 5. So here I'll label this as 2 over 5. And similarly for blue, there'd be 3 out of 5. So your chances of drawing blue in the first is 3 out of 5. Chance of drawing white in the first is 2 out of 5. But now, look at this. So if we draw white again, since we already drew a white, your denominator decreases by 1 because now there are 4 inside the box. So this would be out of 4, and there's only 1 white left in, so it'd be 1 out of 4 chance if you already drew the white you first draw. Similarly for blue, well, there are still 3 left in there, but yes, the denominator is still 4 because we picked out that white and didn't put it back in the box. All right, so now for blue then white, again, the denominator is going to be 4. But in this scenario, we didn't pick a white, we picked a blue, so 2 blues still remain. But for the blue scenario after picking blue, there are 3 blues total, but we picked 1, so there's 2 left in out of the 4 that remain. So this is 2 over 4. Okay. So now if we multiply these probabilities, we'll actually get the probabilities for those scenarios. So here, if you multiply 2 over 5 by 1 over 4, you get 2 over 20, which actually reduces to 1 over 10. For the second one, 2 over 5 times 3 over 4 is 6 over 20, which reduces to 3 over 10. For the third one, you get 3 over 5 times 2 over 4, which is also 6 over 20, which also reduces to 3 over 10. And for the last one, that's also 6 over 20, that's also 3 over 10. All right. Now, yes, so similar to what we did over there, we're being asked to find the probability of drawing white in the second draw. So that's either this scenario or this scenario for drawing white second. So, similar to what we did over there, we are going to add the results of either, because the multiplication principle of not counting, but I guess of probability, really the probability of a union of 2 sets. Either this one or that one. So either one of the 2 possible events will occur. And we saw in 8.2 that just amounts to adding those probabilities minus the intersection, but here there's no overlap of possibilities. So what we end up getting is 1 over 10 plus 3 over 10, which is 4 over 10, which reduces to 2 over 5. So the probability is 2 over 5. Now, a lot of really nice things happen that'll give us kind of deep insight for later on. So let me just say them now that we're here. So notice these, if you add all of these, well, they all have over 10. So just adding the numerators, 1 plus 3 plus 3 plus 3, that's 1 plus 9, so it's 10. And 10 over 10 is 1. And that'll always happen, actually. If you add all of these, all the probabilities will amount to 1. Similarly, and actually, it's pretty interesting to see. If we look back here, we could have actually used this to answer the question. Because how many total possibilities were there? There's 2 plus 6 plus 6 plus 6, that's 20. 20 total possibilities, and for drawing white second, it's 2 plus 6 is 8. And what's 8 over 20? It's the same as 2 over 5. So, in fact, we could have used this argument to get to the probability right away. And this is one reason why I think tree diagrams are a little bit, I don't want to say a waste of time, but, well, let me just say this. They're visual. They're very visual and they'll help a lot. But we have a little bit of a better way of solving these types of problems that we'll discuss right now, in fact. All right, so for conditional probability, we say that the probability of A given B, so this vertical line means given, is the probability of the event E given that B has already occurred. So A given B just means that B already happened. How does that affect A? And it may affect A quite a bit, actually, but we'll see that shortly. In fact, we'll take a look right now. So this is basically the main equation we're going to be using here. And I'm going to try my best to justify this. There's actually quite a number of ways we can justify this. And I've written a Venn diagram here to assist me in that. So here, let's just read it off. So it says, The probability of A given the B already occurred is the probability of the intersection of A and B divided by the probability of B. Now, just to understand what it means to be a probability, remember you divide by the number of elements in the sample space, because that's kind of our universe in some sense as far as the total amount of things that can happen given our particular situation. Whether that comes to the amount of ways you can roll 2 dice or the amount of ways you can draw 5 cards from a 52 card deck, whatever the case may be, the total amount of things you can do, those are elements of the sample space. Now, given that B has already occurred, that means B would now be our sample space. So what that kind of means is that to find the probability of A, given that B already occurred, if B is our sample space now, we're dividing the number of things in A that exist in B by the amount of things in B. So I guess I could do a little bit of shading here, but what it kind of comes down to really is comparing this image to now this image. So this right here, the probability of A, if B is a sample space, would be this. The probability of A given B would be the number of things in A divided by the number of things in B. But there is a condition here. Here it looks like A is a subset of B, and they may not necessarily be the case actually. So for that reason, we're only going to divide the things that exist in B. So in reality, this set here, A, may actually extend outside of B. So really we just want to divide the number of things that are in A and also in B by only the number of things in B. So imagine dividing this shaded region by this blue shaded region, which is all of B. So dividing the thing colored twice by the thing that's only colored in blue, basically. All right, so now that we have that idea down, that's really it, but let me just say this. If this is the number of things in A and in B, because it has to be completely in B, but also in A, from the reasoning we just spoke of, really. Well, if you divide top and bottom by the number of things in the sample space, number of elements in the sample space, on the top, you'll just get the probability of A intersect B, and on the bottom, the number of elements in B divided by the number of elements in S is just the probability of B. So there we go. So this is kind of the same as this when it comes to numbers, and in fact, that's probably a better way of evaluating a conditional probability, but it just kind of goes to show that they're the same. So you know what? Just in red, let me write that over here. This is also equal to, coincidentally, the number of things, number of elements that is, in the intersection divided by the number of things in the set that has already occurred. So consider this to be the denominator, basically. That's kind of the best way of thinking of it. Now there's an alternate form, there's an alternate way of writing this. If you multiply both sides by the denominator here, you get that the probability of the intersection is equal to the probability of what was in the denominator, the set that already occurred, multiplied by the probability of A given B. Now, what I'm about to write is a little strange, but just try to follow me a little bit. So what if we swap these? What if it was, instead of A given B, what if it was B given A? Well, then this would be the probability of, so imagine swapping all A's and B's, then this would be the probability of B intersect A, which by the way, B intersect A is the same as A intersect B, and the denominator here would be the probability of A. So in fact, if you were to multiply both sides by the denominator, you would now get this. Probability of A multiplied by the probability of B given A. All right, so these are the two versions of what is called the product rule, which is just a rewriting of this equation for the probability of a set given another set has already occurred. Now what we're going to do is we're going to try to put this to the test here and apply it to the previous example we saw. That is part 2 of the previous example we saw. I want to find the probability of drawing a white ball on the second draw from a box with 3 blue and 2 white balls. So we're drawing in succession and again without replacement. So really we're just repeating the same example, but now we're going to apply this formula here instead of what we saw with the tree diagram. So here's what I want to say. I want to say the probability of getting white on the second draw is the same as blue first then white, or white then white. So these are kind of the two scenarios, and you can't do both. So for that reason, these sets are mutually exclusive, these sets, that is. So with that being said, the probability of one or the other, if they're mutually exclusive, is just the sum of those probabilities. So all we need to do is just add those probabilities. So this is going to be the probability of drawing blue and then drawing white on the second, plus the probability of drawing white on the first and then white on the second. So the way I'm going to write that is like this. So let me label them as W, well, I guess let's do blue on the first. So let's write B1 as blue on the first. And, so intersection, W on the second. So I guess we could label these as like this, just so we know which one occurs first. So the one that's subscribed by 1 just means that occurred first, and the one that's subscribed by 2 just means that that one is from the second draw. So here this will be, well, white on the first one and white on the second one. All right, so all we need to do now is apply this product rule with each of these in mind. So the first one here, let me write it like this. This is going to be the probability of, we can write it however way we want, in fact, but you have to remember what really this means. So we're drawing blue first, and then after that we're drawing white. So we're drawing blue, and so multiply by the probability of drawing white, given the fact that we drew blue on the first one. Similarly for this one, it's going to be the same thing here. It's going to be the probability of drawing white on the first, multiplied by the probability of drawing white on the second, given that we drew white on the first. Which I know sounds a little bizarre, but once I actually write these out as probabilities, you'll kind of see what I mean. In other words, when I write them as fractions. So as of right now, it kind of seems like tree diagrams are where it's at, really, but once you get the hang of this, it actually goes a lot more smoothly. So the probability of drawing blue on the first is 3 out of 5. Multiplied by, if you already drew blue on your first draw, and there is no replacement, then that means your new denominator is 4 now, okay? Multiplied by, well, what's going to be on top? What are we drawing? We're drawing white, given that we already drew blue. So there are still 2 whites left. So this is 2 over 4. Plus, because of this, probability of drawing white in the first is 2 out of 5 balls. 2 whites out of 5 total. Multiplied by this one, the probability of drawing white on the second, given that we already drew white in the first, well, means the total amount of balls in the box is going to be 4, which because we took one out already. And since we took out 1 white and there were 2 whites total, there's 1 left. So this is 1 out of 4. There it goes. So once we can kind of see this scheme here, we don't have to draw the tree diagram anymore. This takes away the visualization. And in fact, this is the same exact thing we arrived at from doing it visually with a tree diagram. Now notice there's cross cancellation a few places. Well, here there's cross cancellation, and here there's just straight up and down cancellation. So we end up getting this 3 over 10 plus 1 over 10, which is 4 over 10, which is 2 over 5. And that's exactly what we got from the previous result using the tree diagrams or the probability trees. All right, I want to do one more example of this before we move on to the next topic. So let's take a look at that. All right, so for this example here, we are given the 2 cards are drawn in succession without replacement, kind of like the previous scenario we had, from a 52 card deck, and we want to find the probability that each of these 2 events occurs. Now the scenario that comes to my mind is Texas Hold'em, because in that game you actually draw 2 cards, one after the other, of course. And without replacement just means you don't put them back. So after you draw one, then you draw the other, and you keep the one you just drew. So what that means is that the deck goes down, so it decreases the amount. So it starts with 52, but then after the first draw, it's now 51, and so on. And yeah, so that's all we're given here. So we start with 52 cards, and then we draw 2 in succession from the 52. So here we say we want to draw a queen, then an ace after the fact. So let's see. So we want to find the probability of drawing a queen for the first draw, so Q1, and draw an ace on the second draw. So remember, this is the probability of drawing a queen first, multiplied by the probability of drawing an ace second, given that we drew a queen first. From the language we developed from the previous example anyways, Now, what's the probability of drawing a queen on your first draw? Well, there are 4 queens in the deck currently, out of 52 cards total. So there we go, that's this first probability. Now, given that we already drew that queen, that's 1 card less in the deck. So now, this probability is going to be divided by 51 instead of 52 cards, because there's 1 less, of course. And if we draw an ace, well, we drew a queen. It didn't affect how many aces there are. There are still 4 aces. Remember, there's 1 for each suit. So that'll be 4. Perfect. So what we end up with here is just this, and if you multiply straight across, you'll get the answer. But we can reduce a little bit. Let's see, this is 1 over 13. And then if you multiply these together, you'll get 4 over, I'll have to use my calculator on this one. And I got 663 for the denominator. This, by the way, is about 0.0006. I may have said too many zeros. 0.006, which is about 0.6%. I think that sounds better than the fractional way of writing it, even though I prefer that. And in fact, it's probably more useful. It tells you this is pretty hard to pull off. It's less than 1% chance that this will actually happen to you. If you have a deck of cards lying around, you could, of course, try this and see how many times you pull this off out of 100 experiments, and chances are it'll be less than 1 time on average. Anyways, moving on to this one. Let's see if this is more likely or less likely. So here we want to draw 2 queens. So 1 and then another. So let's see. Probability of drawing queen on the first draw and a queen on the second draw is equal to the probability of drawing a queen on the first draw multiplied by the probability of, let's see, drawing a queen on the second draw, given that we already drew a queen on the first draw. Perfect. So remember, the one that's given is what's multiplied over here. So here it was given Q1, so we're multiplying that by the probability of Q1. Good. So now what is this equal to? Well, let's see. The probability of drawing a queen, we already saw that. That's 4 out of 52 for the first probability. Good. And now, again, since we already drew 1 card, our amount in our deck decreases by 1 from 52 to 51. Also, since we already drew a queen, there aren't 4 queens in the deck anymore. Now there's 1 less, so there's 3 total. And now, in fact, this actually reduces a lot. So as it turns out, well, 4 goes into 52 13 times like we saw. 3 goes into 51, believe it or not, 17 times. And if you multiply this, you get 1 over 221. And if you want to approximate that, that is about, I got 0.0045. That may not fit on the board, barely fits. But that's about 0.45%. So it's actually less likely to occur. They're pretty close. They're probably almost equally likely in practicality, but technically, mathematically speaking anyways, drawing 2 queens is harder to pull off than drawing a queen than an ace. All right, so with that said, now we're going to move on to one more topic here. I'm done with the examples for conditional probabilities, but now we'll talk about independence, and we'll see what that's all about. Here we say 2 sets A and B are independent if the outcome of one set does not affect the outcome of the other set. In other words, as far as probability of one given the other goes, if one of the probability of A given B, for instance, if A and B are indeed independent, then no matter what happens with B, if they're independent, then the probability of A given B will just be the same as the probability of A, because it doesn't care what happened with B. They're completely independent sets. So in other words, B occurring does not affect the outcome of A. The probability will be the same no matter what. Oh, also, since they're independent, it actually works the other way around as well. So the probability of B given A is just the probability of B alone. Now, as a consequence, if A and B are independent, then we get this product rule. So let me write this as product rule. So if you take a look at the product rule that we had labeled previously, it said the probability of A intersect B is equal to the probability of A multiplied by the probability of B given A. But if they're independent, then the probability of B given A is just the probability of B. So there you go. And in fact, this is what we'll be using to find out if 2 sets are indeed independent. But usually you can kind of figure it out just by thinking of the situation. Here I give an example, but before we get to this, I need to say that otherwise, we say that the sets are dependent. So that is, if this is not equal to that, so if the probability of B given A is not equal to the probability of B, then they are not independent, so we call them dependent sets. So now onto this example, it says in 2 tosses of a single fair coin, meaning that the probability of getting heads or tails would be the same, so it's 50-50 chance, so each of the probabilities is 1/2. So let me denote that here. So this means that the probability of heads is equal to the probability of tails, which is 1/2. That's kind of what we're going with. And for part 1, it says, show that heads on the first toss and heads on the second toss are independent events. Now this intuitively makes sense, because no matter how you do on your first toss, the probability of getting heads on the second toss will be the same. It's not like drawing cards, because when you draw cards, especially without replacement, well, the deck decreases and changes. But when you toss a coin once and then toss it again the second time, it's still the same coin, it's unchanged. In fact, the same goes for rolling one die. If you roll a die multiple times, the die doesn't change. Drawing cards is different, because when you draw a card from a deck, the deck decreases by 1 each time you draw a card, unless you replace it. Same goes for picking marbles out of a jar or something like that. Now for this scenario, we basically want to use this to test that these are indeed independent sets. But to do that, I want to kind of show you a different way of seeing this. So we can actually write all of the possibilities as one set. So I'm going to write them by basically letters. So HH represents getting a heads on, well, both tosses. HT represents heads on the first toss, tails on the second. TH is tails on the first, heads on the second. And TT finally is tails first and tails on the second. So these are the only 4 possibilities when flipping a coin twice. And it makes sense that there are 4 possibilities, because since there are 2 outcomes for one coin toss, and you're playing that coin toss twice, you're doing 2 coin tosses, that is, it's 2 outcomes for 2 tosses, so 2 times 2 is 4 total outcomes. Okay. So the probability of heads on the first and heads on the second just means the probability to get heads for both tosses, and that's just this one out of these 4 total. So notice the sample space here has 4 elements, but there's only 1 element that has heads for each toss. So this is just 1/4. So for our first coin toss, the probability of getting heads on the first one is 1/2, and similarly the probability of getting heads on the second one is also 1/2. So this goes the same for probability of H2, 1/2. And notice when you multiply 1/2 by 1/2, you indeed get 1/4. So these 2 multiplied is the same as the probability of their intersection. Also, if you look at this here, well, the probability of getting H on the first toss is these 2 out of 4, which reduces to 1/2. Probability of getting H on the second toss would be these 2, which is 2 out of 4, which is also 1/2. So there are a few different ways of thinking about it. Now this second part here we kind of already answered. It asks us to find the probability of resulting in heads for both tosses. So we already did that, so we just want to find the probability of getting heads then heads, basically. Or you can write it like this: heads on the first toss and heads on the second toss. But this, I think, sounds better. So since we already know they're independent events, all we need to do is multiply each of their probabilities. The probability of resulting in heads in the coin toss is 1/2. So 1/2 times 1/2 naturally is 1/4. And there it goes. So the answer here is 1/4. For the first one, by the way, this was just showing that they're independent. And the question says to show that they're independent, so it's kind of already telling the answer here. So there wasn't really anything to box for the first one. So I'm going to go a little further with this, and we're going to do something a little different. It's actually going to involve coin tosses, but we're going to take it to an extreme. So let's take a look at that right now. So although it may seem kind of silly, what we're going to discuss here is basically what we just finished discussing, so independent sets. But with multiple sets instead of just 2, we can have 100 or something like that. So if you have these sets E sub 1 through E sub k, and they're each independent with each other, so they're all individually independent sets, then we can say that the probability of the intersection between all of them is just equal to the product of their probabilities. So if we can determine if sets are, well, independent, then to find the probability of one and the others, right? One, then and this one and that one and so the intersection of all of them basically, all we really need to do is multiply their probabilities. So here, to find the probability of landing all tails in 8 tosses, well, remember, the probability of landing tails in each tosses, so it's going to be tails and tails and tails. So in the first toss, second toss, third toss, all the way to the 8th toss, tails. This is just multiplying each of their probabilities. Now, since the probability of landing a tails is 1/2, we're going to multiply by 1/2 by itself 8 times. In other words, we're going to take 1/2 to the 8th power. And the same can be said for landing all heads, actually. If you have a mixture of heads and tails, though the probabilities are each 1/2, it gets a little fishy because landing a heads then a tails is different than landing a tails than a heads, as far as they can occur multiple times. So if you land 3 heads and 4 tails, it doesn't tell you which order they occurred. So there's, as far as which order they can occur, there's multiple cases. Kind of like we saw when I wrote that set earlier, HH, HT, TH, and TT. There were 2 that involved 1 heads and 1 tails, HT and TH. So the probability of getting the heads and the tails isn't 1 out of 2 times 1 out of 2, it's 1 out of 2 plus 1 over 2. So you have to be kind of careful there. But if they're all the same, then we can definitely pull off this trick. This is the same as 1 over 2 to the 8th. 2 to the 8th is 256. And this is approximately 0.0039, so we can round it to 4, which is about 0.4%. So it's pretty low. Now here, this is kind of similar. It's a little weird to think about though, because it kind of contradicts what I mentioned earlier, but not really. You have to think about the situation a little bit. So here they're asking us to find the probability of rolling a 2, then a 4, then a 5, then a 3 in succession with 1 single dice in 4 rolls. So we're rolling a dice 4 times. We first roll a 2, then a 4, then a 5, then a 3. So it's very specific. So if I had said here, you get 3 heads and 5 tails or something like that, the order matters because you can get 5 tails and 3 heads, or however I said it, in different orders. But here the order is very specific. So here we want to find the probability of rolling a 2 and a 4 and a 5 and a 3. And this is the same as the probability of each one of these all multiplied together. Now the probability of rolling a 2 is 1 out of 6 possibilities in one single roll of the dice. And the same actually goes for 4, 5, and 3. There's only 1 4, there's only 1 5, there's only 1 3. So in every single dice toss, each of these probabilities of landing these numbers is each 1/6 in its own right. So with that being said, this is just 1/6 times 1/6 times 1/6, which is the same as 1/6 to the 4th, which is 1 over 6 to the 4. 1 over 6, well, let's see, 6 to the 4 is 1296. And 1 over 1296 is, I got 7.716 something 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 e to the negative 4. Now, e to the negative 4, if you recall, is just scientific notation. So the calculator is trying to say times 10 to the negative 4. So in reality, this decimal is really 4 places to the left. So if you bounce this over 4 places to the left, you have 3 gaps here. So in reality, this is approximately 0.00077. So if you round it to 8, in percent, that's 0.08%. Extremely low chance of that happening. Now, if you wanted to find the probability of rolling a 2 or a 4 or a 5 or a 3 in 4 rolls, then you would add these probabilities because, well, it's or, not and. And yes, they are independent, and yes, there's no intersection. So for that reason, you can kind of compare the multiplication rule versus the addition rule that we saw in the previous section. In other words, unions versus intersections. For unions, you need to worry about, well, the intersection as far as the sets being mutually exclusive, whereas with multiplication, you have to worry about conditional probability, meaning if the sets are actually independent or not. So there's a nice correspondence there. Anyways, that's it for this example, and that's all I really wanted to say for 8.3. We didn't do too many examples like usual, but again, the examples we saw I think are pretty fitting in what we'll be seeing as far as homework problems go. Anyways, I'll see you in the next video for 8.4. Thanks for watching.